have Professor Dieter with us, and so we are interested to hear a bit. What is your opinion about quantum computing, like the intersection between quantum computing and fluid dynamics? Like, how do you find it?
So the intersection between the two fields is that both of them are kind of physically challenging problems that basically require a lot of expertise and a lot of kind of modeling and physics knowledge to be solved. And beyond that kind of generic scientific expertise that one needs, both of those fields have a challenge in how many parameters, how big the problem is that needs to be solved. And so it's basically in both cases always a question of how do we handle large amounts of data and information in an efficient way and get out the solutions that we're really interested in.
And so what are the current challenges in realizing industrial quantum CFD algorithms?
I think the main difference between the quantum algorithms or the quantum problems that we're usually solving and the industrial applications is that those are even more complex in their setup. So not just in principle in the modeling itself, but in how then the various different problems need to be adapted to the actual situation of interest, whereas in physics or in quantum computing or in any of the work that physicists usually do, you can make certain approximations and simplifications to make things solvable and gain basic understanding. Here it's really about very specific problems that have added complexity through them being part of what is realistically needed in and outside of physics world.
And to finish, so what is the biggest misconception people have about quantum computing for engineering?
Oh, I think the biggest misconception is not just in quantum computing for engineering, but it is generally that you can take a quantum computer, program it as if it were a classical computer, and would just run everything much, much faster. So indeed, quantum computers work fundamentally differently from classical computers, and they need a different way to be programmed and a different way to be to develop algorithms on. So we can't just take what we know from classical computers and one-to-one translate it to quantum computers and expect an improvement. We need to think differently. And that's, I think, the biggest misconception, that you could just take what you know already and just translate it straightforwardly.
So here with us, we have Professor Angelakis from TU Crete, who is also the director of Athens Quantum Institute. Can you tell us a bit more about this place?
Yes, so it's great to have you here for the coordination meeting, the whole quantum CFD project. We are at the Athens National Center for Research called Demokritos, and this is a collaboration between TU Crete and the Athens Institute to host you here at this conference.
So what is your role in the European QCFD project?
We work very closely with a team in Hamburg and also the experimental teams to develop the algorithms closer to what experimental devices can do at the moment. So we are responsible for leading the work packages that take their abstract mathematical algorithms and make them viable for quantum devices.
And what is the most exciting contribution in the project?
That's a very good question. We had actually a demonstration very recently where our results were implemented in European quantum computers made in Austria, and they managed to really reproduce a large scale of a large part of our predictions for observing fluid dynamics in near-term quantum devices.
And how do you see the evolution of the field of quantum computing in Greece and in EU in general?
It's an exciting question. I mean, Greece is entering the race, hopefully not so late, with their activities in participating into this quantum flagship project. We hope there will be more, and especially with the investment now in the newly established Quantum Institute here in Athens, that the focus will be in quantum computing and technologies. We want to focus more on the algorithmic and the software developments, including applications for certain use cases relevant to the national and to the EU ecosystem. We'll be building some devices as well, and I think it's a great time to really do quantum in Europe as things are going at the moment.
So we have a pleasure to have with us Eugene from NGS. So first of all, let's hear a bit more about you, like the company. What are you doing in NGS?
So we're ISV. We make CFD software and sell it mostly in the motorsport industry. So our biggest customer base basically is Formula One. So we work in a very dynamic and exciting world.
And how you got involved in the QCFD project?
Ooh, well, I think it was Thomas Rung's fault. So we always wanted to work together, and I think it was just well, it was just a bit of luck, really. We were the right place, the right time, with the right set of expertise to complement the project, and yeah, I think that was, as these things happen, you know, you connect, and then you get lucky. But you have to be right. You have to be ready to be lucky, right? You can't just hope to get lucky, and then yes.
And so far, how did you find the project? How is it going?
Oh, it's very interesting. I mean, you know, physics was something I've always been interested in since I was a kid. But in South Africa, where I grew up, doing a career in physics wasn't really considered very viable. So I got into engineering, and so this is the first time I've gotten involved in something like this, and it's been more complicated than I thought.
Yeah, I totally understand because I'm from Mauritius. We are neighbors. So last question. So what are current challenges that you can already see from an industrial point of view?
In terms of QCFD?
Yeah.
Wow, there's a lot. The paradigm that we're trying to engender here, right? We're looking at really doing away with models in a big way, whereas in the current engineering approach, there's a lot of models, and there's a particular way of looking at the problem and dealing with the problem. So I think we've already seen some communication that we have to forget about looking at the colors, or we have to at least think about less detail and more integral feedback to the problem, whereas in the current engineering context, people are very much integrated into the solution, so they can see, they can gain intuition and experience. So there'll be quite a big difference to get these really fast but really accurate results with very limited modeling, but also to have much less insight into the detail of what's going. So it's a much blacker box if you want to think about it. So that will definitely take some getting used to, I think.
Thank you.
Thank you, Jean.
So we have the pleasure to have with us Professor Rong from TUHH. So today we are interested to hear what he has to say about the QCFD project. And so let's start with the first question. So what is the motivation for your interest in quantum computing?
Well, generally, CFD is an established high-performance computing strategy, and it's very well known to many engineers. Has connections to energy, technology, aerodynamics, marine engineering, and geosciences. However, classical methods that we use today are limited very much in terms of the exponential increase of demands in memory and compute time. And if we want to resolve more of the flow for future designs, the associated time to cost and the associated storage requirements are far beyond the resources that are offered by classical methods.
Yeah. So what are the opportunities that you see in the use of quantum computing?
Well, the major opportunities as compared to classical hardware are the more energy efficient resources and the incredible amount of storage that quantum computers offer. In fact, they offer an exponentially large vector space, and this promises a reduction in both computing time, energy efficiency, and also storage requirements as compared to classical methods. And this is basically the major motivation for us.
And so how far is your research from technical application?
Well, admittedly, the project started at relatively low, what we call TRL or technical readiness levels, probably in the range of TRL2, which is the concept phase, or TRL3, which is the proof of concept phase. And we now aim at finishing around TRL5 to 6, which will bring us into the position that enables us to develop and validate first simple application for technical flow problems, including the boundary conditions and operating conditions that you typically meet in engineering practice.
Nice. And so another question. So what fascinates you the most about the QCFD project?
Well, for me as a curious engineer, the most fascinating thing is the very strong network between physics and engineering researchers, and furthermore, the high level of IT competencies that is reflected by all of us.
So a tough one now. So what is tough when performing QCFD?
The toughest thing is understanding each other. I mean, technically speaking, the really challenging thing are, of course, the efficient treatment of, say, dissipative and nonlinear terms. But apart from that, really understanding each other across the various disciplines is a very tough thing.
And to finish, so name 2 key issues of your research.
Probably the 2 key issues I would mention are boundary conditions and complex geometries.
Hi everyone. Today we have the pleasure to ask questions to Paul Over, who is a doctoral researcher at the Technical University of Hamburg, Harburg. And we have prepared some questions on the QCFD project, and he will give us his insights.
Thanks. Yeah, of course.
So Paul, how would you describe a quantum computer to CFD, Computational Fluid Dynamics engineers who have never used one before?
That's a really good question. In general, a QC, or a quantum computer, is a new type of computer. It's based on principles of quantum mechanics, and instead of discrete bits, like 0 and 1, information can be encoded continuously by leveraging qubits. This implies that the process of information that scales exponentially with the qubits, and in this case, is different to that on the quantum or in the classical computer.
I see. So how does this relate to, so then if you take this and you go now, how are these quantum computers classified from a CFD engineering perspective?
Okay, I mean, as we had just started development of quantum computers, the current quantum computers are small and noisy, and they are generally referred as noisy intermediate scale quantum devices. NISQ is the abbreviation for that. And they are only capable of implementing really shallow circuits because, in general, such devices are experiencing decoherence time, which basically limits the depth in general. And such devices are often used in part of hybrid classical quantum configurations, where we use a classical computer next to the quantum computer, and then set up kind of optimization problem. And there the classical computer then controls the optimization procedure, while the quantum computer composed or takes care of the most computational demanding task. The other group, which is not really as ready as the NIST devices today, is known as fault-tolerant devices. These rely on quantum error correction protocols and expected to become available in the near future. So that will be the next generation of quantum algorithms.
Interesting take. So let's move further and ask you the question. So right now, what do you see? What are the biggest challenges when translating the classical algorithm or the classical CFD algorithm to the new quantum paradigm? So what steps are necessary there?
Okay, I mean, in general, when we have the CFD algorithm, we rely on classical operations to do that. And here, first of all, QCD operations are by definition different and are in that case linear and norm preserving, which is a huge difference to the classical, and which implies here that only unitary transformation can be applied deterministically. This requires then redeveloping or developing algorithm from the scratch, which fits the characteristics from the quantum computer in order to guarantee a quantum advantage and also to realize what we now know from classical computational fluid dynamics. To this end, all the fundamental methods which are well established in CFD, such as including boundary conditions or treating nonlinearities or implementing upwind bias schemes for treating convective kinematics, need to be rewritten. And this is basically this step, which is majorly important.
I see. So moving further, so how do you see like the main objectives of this project? What are the goals? What should come out at the end of the project?
I mean, in general, I assume you are a physicist and I'm an engineer. This is, I think, one principle of the QCFD consortium, that we are really like a multidisciplinary consortium, and this is a really multidisciplinary collaboration, which allows us to bring together engineers, theoretical and experimental physicists, and we all work together with the idea or with the goal of expanding the applications of quantum computers or on quantum computers to some industrially relevant engineering problems beyond quantum mechanics, which have been already covered quite often. And the versatile algorithms, frameworks are especially there for solving a wide array of CFD problems. They undergo extensive validation in this consortium after a interesting and really challenging brainstorming and development phase. And then after that, and after the validation, of course, we perform many benchmarks. And also this will be provided then with quantitative information for any hardware requirements and will be assessed in that sense.
I see. Thank you for that answer.
Yeah.
Why is it important to explore quantum computing for CFD today, even though the hardware is not fully mature yet?
Good question. I think in general, exploring quantum computing for computational fluid dynamics today allows us to develop and test new algorithms in parallel with hardware advancement. And this ensures that once scalable, reliable quantum computers become available, that we are ready to use them for engineering problems to fully exploit their potential.
Thank you. So, what is, in your opinion, the future of quantum computers?
Okay. I mean, despite fundamental challenges such as I/O problems and I/O data management, the effect of the success probabilities of dissipation, we believe that this has an enormous computational potential of QC and will lead to the next technological revolution, not only in academia, but also in industry, and especially when they are then combined with artificial intelligence.
Interesting. Oh, thank you. We have now the pleasure to interview Spiros Cherkis, who is a senior researcher at the Technical University of Crete.
Hello. Thanks for having me.
How was working in a multidisciplinary team, engineers, physicists, mathematicians, has shaped your approach?
As a physicist, I started working on pretty specific problems in the beginning, but when I started working on quantum computing, and especially in QCFD, I had the pleasure working with people from multiple backgrounds, and that was pretty interesting because I learned things that otherwise I wouldn't have the chance to learn. And especially the Technical University of Crete has a specialization on computing and optimization. That was something relatively new for me, and I gained a lot of experience working with them.
I see. Thank you. What is your specific role and contribution within this project?
So in this project, I work on the optimization of quantum circuits. The idea is that problems in QCFD are mapped into quantum computing and circuits that we have to run. Sometimes those circuits are too long and too deep, and that accumulates a lot of noise. So my project was mostly focused on how to make them shorter in depth in order to gain in terms of noise.
I see. That's an important contribution. What is your background and how is it relevant to the QCFD project?
So I'm a physicist. I started my career in quantum computing as with a bachelor in physics, and then I moved into quantum information. Quantum is mostly on entanglement theory. Entanglement is the resource for quantum computing, and soon I got involved into how noise is involved into entanglement and in general in quantum information. Due to my involvement in a quantum startup that was on quantum computing and optimization of quantum circuits, that's how I got involved with QCFD, and that's why my current research is relevant to the optimization of quantum circuits.
I see. How would you explain your research to a person outside the field of quantum computing, CFD?
Yeah, that's a tricky question because it's a specialized topic. I guess I would say that it's an engineering problem, the problem that we're trying to tackle. And this type of problem suffers from noise. So the question is, how can you remove noise in order to make the simulation and the application works better? So the problem is well known. It's fluid dynamics. We have to solve difficult differential equations. So the question, how can we do that efficiently with quantum computers?
would you say to a young researcher considering entering this field?
I guess I would advise a young researcher to keep it as broad as they can in the beginning, to learn as much as they can and specialize later on, because it's a multidisciplinary field and maybe it's better in the beginning to learn and later to realize what you're more interested in and what you can contribute.
I see this. We have now the pleasure to interview Tomohiro Hashisume, a senior researcher from the University of Hamburg.
I'm pleasure to be here.
What has been the most surprising or unexpected findings in your research so far?
I would say that it was very surprising that quantum-inspired methods, which were developed to simulate quantum systems, become so useful for simulating classical field and classical dynamics in such a way that that in some cases overpasses the classical pre-known algorithms, and that really surprised me, and that motivated me to be in this field.
That's an interesting insight, Tomohiro. How do you see the relationship between the classical and quantum algorithm? Do you rather see it as a replacement or as coexistent?
Probably the reason why the quantum computing is not very popular at this time in the moment is because the classical computing is so powerful. You can do billions, you can manipulate billions and billions of numbers in just a flick of a second, and that's impressive in the classical computing side. So for the next few years, or maybe few decades even, it's gonna be classical computing and quantum computing taking hand to hand and developing together towards a more energy efficient and fast computing regime that quantum computing can truly truly achieve, I guess.
What do you think makes quantum computing interesting for fluid dynamic problems, in your opinion?
I think currently the field's consensus is that we could never directly simulate exactly the flow around massive objects such as airplanes and cars with classical computing, but quantum computers, because of its properties, there is, and we see the verge of the possibilities that we can actually perform this exact computations without waiting for us for the age of the universe.
What is your background and how did you get involved in the QCFD project in the first place?
So my background is in quantum information and this thing called quantum information scrambling in quantum systems. And turns out this kind of chaotic dynamics and information structure that quantum circuits creates is highly relevant in the context of quantum computing and understanding the computational capacity of quantum computers. So that's how I got interested in and decided to be involved in this particular project.
It's fascinating, this connection from your theoretical work to this classical real-world application, I would say.
Yes.
What do you see are currently the challenges in realizing industrial quantum algorithm for CFD? What steps or adjustments need to be done to achieve this goal?
So at the verge of classical computing, there was massive incentive by various nations to create a huge computing facilities with a room full of computers made of vacuum chambers. And I think something similar must be done with quantum computer. We must put quantum physicists' effort together and create room full of quantum computers so that we can have technological advancement on hardware side, as well as because we should be able to do a lot of trial and errors with huge amount of quantum computers. We should have a huge innovation on software side as well. So I think we need to do this kind of massive trial and error kind of experiment on quantum computing as well.
We have now the pleasure to interview senior researcher at Planck, Alexios Michaelidis. Welcome.
Nice to meet you.
What excites you the most in the field of quantum computing for CFD?
I think it's a new field with many interesting opportunities to innovate and provide new solutions for the industry and academia.
What is the biggest misconception people have about quantum computing for engineering applications?
Yeah, developing algorithms for engineering, using quantum computing algorithms for engineering requires to think all the way from scratch. So it's not as simple as it is to develop it for classical computers, where you have many years of experience on how to develop the algorithms themselves.
What has motivated you to work at the intersection of quantum computing and fluid dynamics?
I think, well, I was already working in the field of quantum computers, and it was an interesting adventure to explore how it applies to fluid dynamics and what we can, improve there through quantum computing.
What has been the most surprising or unexpected findings in your work so far?
I think generally it's very hard to predict when something will work and when something is not going to work. So many times you are surprised that something works, and sometimes you are surprised that something doesn't work.
We have now the pleasure to interview PhD student José Diogo da Costa Jesus. What is your specific role and contribution within this project?
So my role is to think, based on the algorithm, how one can implement these on actual machines that we have available today. How we can design ansatz and mitigation protocols so that we recover a usable result.
So far, what do you see are the main limitations of the current quantum hardware for engineering applications?
The current limitations of quantum hardware for engineering applications is the fact that we don't have perfect gates. As we apply more and more gates, error accumulates, and therefore, when we have a deep enough algorithm, we are completely lost.
What needs to happen before quantum methods can compete with the classical CFD methods that have been optimized for decades?
So the answer to that is clear. We need fault-tolerant quantum computing. So we need a machine capable of detecting that it committed errors and to correct those errors.
That makes sense. Name 2 key issues or problems that you have encountered so far in your research within this project.
So given my role in this project is to try to implement these algorithms in the machines, I would say the main 2 issues are reducing the depth of the algorithm as much as possible and to come up with useful, practical ways to mitigate the noise as it grows in the algorithm.
It's an interesting insight, Jose.
Thank you.